interested in defining the length of a curve. The last example that we saw, that of space filling curves, suggests that we should approach this with a bit of care. It is unreasonable to expect that all curves will have lengths. Those that do are called rectifiable curves, and we now give the definition of this as well as what the length of a rectifiable curve is. So definition. As always, gamma from AB to Rn is a curve. What we are going to do to define rectifiability and arc length is the most obvious thing. So let me first draw a picture to illustrate what's going to happen, then erase the picture and move on with the definition. So the picture is as follows. You have some curve. What you do is you pick points on this curve. And join the line segments in between these points. So I have not drawn it perfectly, but you will get more or less an idea of what is happening. So you draw these line segments together. Now what you do is you know how to measure the length of a line segment. That's just, if you call this vector v1 and v2, the length of this line segment from v1 to v2 is just norm v1 minus v2. So this is what is known as a polygonal path. You just look at the length of the polygonal path. And our intuition is that this polygonal path, the length of this polygonal path will approximate the length of the curve. Then what you do is you just keep adding more and more points, exactly analogous to what you did to define the Riemann integral as the area under the curve. What we did was break it up into rectangles there. So here you break it up into line segments, and as you make these points closer and closer to each other, intuitively the length of the polygonal path will in some sense converge to the length of the curve. That's the basic idea. Now let's make this precise. What you do is the following. Let P equal to T0 T1 ... Tm subset of AB be a partition, and as the notation suggests, we always take T0 to be A and T0 less than T1 less than T2 ... less than Tm, which is equal to B. Exactly like how you defined the Riemann integral, you consider a partition and you order the points in increasing order. Now we define the length of this curve gamma with respect to this partition P to be, as you expect, summation I running from 1 to m, the norm of gamma of Ti minus gamma of Ti minus 1. Okay, so that this is nothing but the length of the polygonal path whose endpoints are determined by this partition. More precisely, the endpoints are gamma of Ti. Okay, now here is the central definition. We say gamma is rectifiable if we can find a number m greater than 0 such that this L gamma P is less than or equal to m irrespective of P. So what this is saying is, no matter what partition P you choose, the length with respect to that partition will be less than or equal to m, and this m is independent of the choice of partition. Okay, so in this event, when it happens that there is such a curve, there is such a constant m, in this event we define the arc length of gamma to be the supremum of L gamma P, where we take supremum supremum over all possible partitions, all possible partitions, I think I wrote too many T's in partition, all possible partitions of AB. So the definition of the arc length of a rectifiable curve is the most natural one possible. You approximate the curve by polygonal parts, and the maximum length of a polygonal path that you can obtain in this way is called the arc length. We will see maybe 7 or 8 videos down the line how this method spectacularly fails for surfaces. You would think that the exact same idea would work for surfaces. Try to approximate the surface not by polygonal parts but by triangular faces or something like that, a triangulation, and approximate the area of the surface by the net area of the rectangles that triangles that you get. That will hopelessly fail. We will see that. Okay, so essentially what we are doing is we are approximating the curve from the inside using polygonal paths and taking the supremum over all such lengths that you get and defining that to be the arc length. Okay, now let's prove some basic properties of arc length. None of these are particularly shocking, and the proofs are more or less trivial because we have already seen the Riemann integral. Yeah, one more remark in this regard. Just like the Riemann integral, the moment you add an additional point, or that is refine a partition, the length with respect to the new partition will be greater than or equal to the length with the original partition. I'm not even going to bother writing this down. The proof is very easy, so please do that. Okay, so under refinement, the length can only increase. We will use that many times in the proofs. So the first lemma is additivity of arc length. This is more or less geometrically obvious but requires a proof. This states the following: let gamma from AB to Rn be a curve, be a rectifiable curve, and let C be a point in AB. Then length of gamma is nothing but length of gamma restricted to AC plus length of gamma restricted to CB. That is, if you break a curve into two pieces and take the sum of the arc lengths, you get the sum. You get the arc length of the whole curve. Of course, this is obviously true by induction even for finitely many curves. Proof. Again, the proof is not at all hard. What you do is you fix a partition. Let P be a partition of AB. Okay. Now add C to this partition if needed. This partition, if necessary, then we can write P as P1 union P2, where P1 is a partition of AC, and P2 is a partition of CB. Right? So you gather together all the points in the partition P that also happen to be in the interval AC. Then you gather together all the points in the partition P that also happen to be in the interval CB and call that P1 and P2 respectively. It's obvious that P is P1 union P2, and P1 and P2 are partitions of AC and CB respectively. Okay, now that you do this, it's clear that the length of gamma with respect to the partition P is nothing but length of gamma restricted to AC with respect to P1 plus length of gamma restricted to CB with respect to P2. The fact that you have equality here just follows by expanding out what the expression for length of gamma with respect to P is, length of gamma 1 restricted to AC with respect to P1 is, and length of gamma restricted to, oh wait a second, this is not gamma 1, that was just supposed to be gamma restricted to AC with respect to P1 plus length of gamma restricted to CB with respect to P2. The fact that these the left hand side and right hand side are equal just follows from the definition of what the length with respect to a partition is. Just write it out, you will get it. Okay, so what this shows is that you can immediately write this is less than or equal to length of gamma gamma restricted to AC plus length of gamma restricted to CB. I'm just using the fact that the length of gamma restricted to AC is the supremum over all partitions. So this shows one side. This shows that length of gamma with respect to P is less than or equal to length of gamma with respect to AC plus length of gamma with respect to CB. So you can take supremum on the left over all the partitions P to conclude that length of gamma P is less than length of gamma restricted to AC plus length of gamma restricted to CB. So that's one side. That's one side. Now we'll have to show the other side, and the other side is equally trivial. Let P1 be a partition of AC and P2 a partition of CB. Consider partitions. Then obviously P1 union P2 is a partition of AB. Okay, and it's also clear that length of gamma restricted to AC with respect to P1 plus length of gamma restricted to CB with respect to P2 is equal to length of gamma P1 union P2. Okay, which is less than or equal to length of gamma. Again, taking supremum over all P1 and all P2 on the left hand side, we get the required result that length of gamma restricted to AC plus length of gamma restricted to CB is less than or equal to length of gamma as required. So this concludes the proof that arc length is additive. Okay, now there is a monumental defect in our treatment of rectifiability, and we are going to rectify it now. It's the fact that I have not provided you any example of rectifiable curves. I will compensate by providing uncountably many examples in one shot. We are going to now show that a C1 smooth curve is rectifiable. C1 smooth curves are rectifiable. Not only that, I'm going to give you a formula for the arc length. Now the question is, what is the intuition behind this and what sort of formula can you expect? Well, for a moment, let's take out our physicist hats and put it on our heads and think like a physicist for a moment. Well, since this is a C1 smooth curve, this has a well-defined velocity vector at all points. The norm of the velocity vector will give you the speed of the curve. This speed will be a continuous function because it's a C1 smooth curve and the speed is nothing but the norm of gamma prime of t. Gamma prime is continuous, norm is continuous, so norm gamma prime of t is continuous. So the speed is a continuous function of t. What could be the length of a curve other than the integral of the speed? So you would expect that length of gamma is nothing but integral a to b norm gamma prime of t dt. So if this were a physics textbook, this would be the proof, but this is not a physics textbook, so we'll have to prove this rigorously. The proof is not hard, it just requires some new concepts. So it will be convenient if I could define in an ad hoc way what the integral of a function into Rn is. The definition is not hard, so let me just do it right here. So for the time being, this is just a convenient definition. There is no, don't assign any deeper meaning to this definition. Let gamma from AB to Rn be a, it need not actually be a curve, it be a function, that's enough. Be a function such that gamma 1, gamma 2, dot dot dot, gamma 1, gamma n are integrable. Where gamma is nothing but gamma 1 to gamma n. So I'm taking a function gamma, writing the coordinates as gamma 1 to gamma n. I'm assuming that the coordinates are integrable. Okay, then we define the integral from a to b of gamma of t dt is by definition just the vector integral a to b gamma 1, integral a to b gamma 2, dot dot dot, integral a to b gamma n. You just integrate coordinate wise. If each coordinate function is integrable, the integral is nothing but the integral of each coordinate and that resulting vector when you put all these coordinate integrals together. Okay, so just I remark again, there is no deeper meaning to this. This is just a convenient definition of integral of a vector valued function. Okay, now let me just prove one basic property of this vector valued integrals, which is going to be used in the proof of the fact that C1 smooth curves are rectifiable. So let me just state a lemma. I'll just call it taking norm inside the integral. So this is a trick which is very commonly used in analysis. You can always, in most situations, take the norm inside the integral and get an inequality. So this is the the lemma is as follows. Let gamma from AB to Rn be as in the previous definition. That is, each coordinate function gamma 1 to gamma n is integrable. Then norm of integral a to b gamma of t dt is less than or equal to integral a to b norm gamma of t dt. You can take the norm inside the integral. Okay, the proof is again not very hard. It's just a straightforward check. Now set v to be integral a to b gamma of t dt. This is well defined simply because each function, gamma 1 to gamma n are assumed to be integrable. Set v to be this. If v equal to 0, then nothing to prove. Okay, so we can assume v is not 0. Assume v is not 0. Okay, now what I am going to do is I am going to apply the Cauchy-Schwarz inequality. You first look at v, the standard dot product, the standard inner product, a to b gamma of t dt. Note carefully, the left hand side is nothing but v dot v. Okay, and just by the way this integral is defined, which is component wise, and just by the way the dot product is defined, this equality, that v dot a integral a to b gamma of t dt, is nothing but integral a to b v dot gamma of t dt. Okay, just check this. Just check that both sides are equal. This just follows directly from the definition of the dot product and the definition of the integral. Okay, now what I do is I apply Cauchy-Schwarz inequality for the term v dot gamma of t to get this is less than or equal to integral a to b norm v norm gamma of t dt. Okay, so here I'm using various basic properties of the Riemann integral, the standard Riemann integral. So I want you to check that this is correct. This is just Cauchy-Schwarz, and this is just norm v integral a to b norm gamma of t dt. Okay, I'm just taking the norm v outside. Now observe that the left hand side, what we started off with, is nothing but norm v squared. So what we get is norm v squared is equal to norm v integral a to b norm gamma of t dt. And of course I can cancel off one of the norm. This is not equal to, this is less than or equal to, sorry about that, this is less than or equal to. So the net conclusion is we conclude that norm v is less than or equal to integral a to b norm gamma of t dt. Okay, and here we could cancel simply because norm v is assumed to be non-zero. So an exercise for you, if you have been carefully paying attention to this proof, this question would have cropped up into your mind. Why is norm gamma of t integrable? We have used that in this, right at the statement level. We have used the fact that norm gamma of t is integrable. Why is norm gamma of t integrable? Think about that. It would be obvious if gamma were a curve, because norm gamma of t would then be continuous, there will be no issues. But since we are not assuming that gamma is a curve, it could be any function which is integrable. This requires a bit of thought. Okay, now we can finally prove that C1 smooth curves are indeed rectifiable. So let me state and prove the theorem. Let gamma from AB to Rn be C1 smooth, then gamma is rectifiable and integral a to b norm gamma prime of t dt is the length of gamma. Okay, so the physicist intuition is absolutely correct in this regard. Okay, so here the issue of well-definedness of the integral does not arise, since norm gamma prime of t is continuous, the integral is well defined. The integral is defined. So there is no issues here with definedness of the integral. So let's start with the partition. Let p equal to t naught dot 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 tm be a partition. As usual, I will always write the partition out in the increasing order. Implicitly, it's implicit in the way I've written it out. T naught is less than T1 dot 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 less than Tm. Fix epsilon greater than 0. Okay. Now, what I'm going to do is I'm going to apply fundamental theorem of calculus in a slightly different way than usual. Look at summation norm gamma of Ti minus gamma of Ti minus 1. Look at this. This is I running from 1 to m. This is nothing but L gamma of P. Okay, the length with respect to the partition P. You can check that a trivial application of fundamental theorem of calculus will tell you that this is summation integral a to b gamma prime of t dt, and I have to put a norm outside. Okay, this just follows by applying the fundamental theorem of calculus to each coordinate separately. Okay, so this is by fundamental theorem of calculus. I'll just abbreviate it to FTOC if you don't mind. Okay, now we can take the norm inside the integral. We just proved a lemma and we are duty bound to use a lemma that appears just before a theorem. So this quantity is less than or equal to summation integral Ti minus 1 to Ti. So one second, yeah, that's correct. This is nothing but summation integral ti minus 1 to ti norm gamma prime of t dt. Okay, which is in fact nothing but integral a to b norm gamma prime of t dt. Okay, so I have just used the basic properties of the Riemann integral to go from this sum to this equality. Okay, going from here to here is just taking the norm inside the integral and applying again some basic properties of the Riemann integral. There's nothing much happening here. Okay, 1 second, I think I have made a typo and that's why I'm sounding a bit confused. This is not a to b, of course. This is not a to b. This is nonsense. This is not a to b. This is ti minus 1 to ti, right? Of course, if I do a to b, I will get a different expression, but not the one that I want. Okay, so here I'm applying the fundamental theorem of calculus on each one of these intervals ti minus 1 to ti. Sorry about that. So yeah, now I'm a bit happy. I was wondering what happened. How did I split that ab into ti minus 1 ti suddenly? It was done in the prior step actually. Okay, anyway, we got this. So what this shows is that gamma is certainly rectifiable, and length of gamma is less than or equal to integral a to b norm gamma prime of t dt. So one side we have shown rectifiability, and we have also shown that the integral of the speed at least is greater than the length of the curve. Okay, now we have to show that this inequality is actually an equality. To do that, what we do is we define the arc length function. So define s of t by definition to be integral a to t, not integral a to t, sorry about that. Define it to be length of gamma restricted to at. Okay, so t is in ab. So we have now defined the function s of t where t runs from a to b. If you at the point t, it just gives you the arc length up until t. Okay, now for h greater than 0, by additivity of arc length, it's immediate that gamma restricted to t plus h, the length of this is nothing but s of t plus h minus s of t. I've just used the additivity of arc length and taken terms to one side. Just shuffled around the terms and you get this. Okay, now once I have this, I can now try to sort of take the difference quotient, the Newton quotient, and see what happens. Look at norm gamma of t plus h minus gamma of t by h. Okay, now this is less than or equal to s of t plus h minus s of t by h. Why is that the case? Well, I just about a minute ago said that this s of t plus h minus s of t is nothing but the length of gamma restricted to t plus h, and this is just, if I take the trivial partition t plus h and find out the length of that curve with respect to this partition, this single term is what I would get. So this single term will be less than or equal to the length, which is equal to this. So that's how we get this inequality. And this, again by the fundamental theorem of calculus, this will be less than or equal to 1 by h integral t to t plus h norm gamma prime of u du. Okay, so this inequality, this was this is due to the fundamental theorem of calculus, but actually this we just proved this via the fundamental theorem of calculus. We have just shown that the C1 smooth curves are rectifiable and their arc lengths are less than or equal to the speed integral. So we get this when applied to the curve gamma restricted to t plus h. So I shouldn't really say by the fundamental theorem of calculus. Ultimately it's by the fundamental theorem of calculus, but this particular inequality is via what we have just proved. Okay, now taking limit h going to 0 plus of this norm gamma of t plus h minus gamma of t by norm h by h, this is clearly just norm gamma prime of t. Check that. This is a trivial check. This is just follows almost immediately from the definition. And this now is the place where I apply the fundamental theorem of calculus. This is nothing but limit h going to 0 plus 1 by h integral t to t plus h norm gamma prime of u du. This part is the fundamental theorem of calculus, this equality. This is f-talk. Okay, so this equality is f-talk. So check that. Now because this term limit h going to 0 plus blah 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 is mod gamma prime of t, this is nothing but the left hand side. Okay, and taking limit h going to 0 plus of the right hand side also gives the same thing. It also gives mod gamma prime of t. So the net upshot is by the squeeze theorem, by the squeeze or sandwich theorem, whichever you prefer, by the squeeze theorem, limit h going to 0 plus of s of t plus h minus s of t by h, this is nothing but norm gamma prime of t. This is just the squeeze theorem. Similarly, we can deal with the case. Similarly, we can deal with the case h less than 0. So net upshot is limit h going to 0 of s of t plus h minus s of t by h is norm gamma prime of t. Okay, but this is nothing but d by dt of s of t. Okay, which is nothing but s prime, the derivative of t. So again, the fundamental theorem of calculus will now tell you that s of b is nothing but integral a to b s prime of t dt. This is because s of a is just 0, as you can see, and this is integral a to b norm gamma prime of t dt. Okay, so this is the proof. It's not too hard. It's just slightly different way by which we apply the fundamental theorem of calculus. We can conclude that the C1 smooth curves are rectifiable and their lengths are nothing but the speed integrals. Okay, so I have now given you uncountably many examples of rectifiable curves. Let me give you one example of a non-rectifiable curve. One might be under the impression that all curves are rectifiable. As the space filling curve suggests, this might probably not be true. This example is significantly simpler than the space filling curve example. Okay, look at the function f of x equal to x cos pi by 2 pi by 2x if x is not 0 and 0 if x is equal to 0. Okay, now first exercise for you, check that f is continuous. Check that f is continuous. Okay, I'm going to claim that the function x going to x comma f of x is not rectifiable on 0, 1. I'm going to treat it as a curve defined on close 0, 1. This is essentially the graph of the function f. As we have remarked when we discussed examples, the graph of a function from an interval can be naturally considered as a curve. I am claiming that this curve x going to x comma f of x is not a rectifiable curve. To do this, consider the partition Pm, which is by definition 1 by k, such that 1 is less than or equal to k is less than or equal to t to m along with the point 0. Okay, this will be a partition of 0, 1, and I'm going to try to find out how f behaves at these partition points. Okay, observe that we have summation I equals 1 to 2m mod f of ti minus f of ti minus 1. This is nothing but summation I equals 1 to 2m 1 by I. As you can check just by substituting the function here, which in this situation is nothing but x cos pi by 2x, you will see that this is true. Okay, now you can now show that x going to x comma f of x is not rectifiable. I leave it to you as an interesting exercise. Essentially, you have to use the fact that summation 1 by n diverges. That's what is going to be used. So this shows that you cannot expect all curves to be rectifiable. There are quite simple curves that we can define which are not rectifiable. Now I'm going to show one more interesting property about arc length. Arc length is now defined for a continuous function. We can now consider the arc length function s of t that we already considered in the proof of the fact that C1 smooth curves are rectifiable. Now it is intuitively obvious that this function s of t itself would be continuous. In fact, that was obtained as a part of a proof. At least for the C1 smooth case, we in fact showed that the arc length is differentiable and the derivative of the arc length is the speed. So these are intuitively physical facts that we were able to prove rigorously. But what is nice is it is true in general that the arc length is a continuous function even when the function gamma is not assumed to be C1 smooth but just rectifiable. So that's the next theorem. This is the continuity of arc length. So the statement runs as follows. Let gamma from AB to from AB to Rn be a rectifiable curve. Let s of t be by definition the length of gamma restricted to AT. Okay, so t is also in AB. Okay, then we have the following facts. Number 1, s is an increasing function. I'm not claiming strictly increasing or anything, it's an increasing function. 2, if gamma is non-constant on any non-singleton subinterval of AB, then s is strictly increasing S is strictly increasing. 3 gamma, not gamma, S is continuous. So this theorem shows the continuity of arc length. So let's see a proof. Proof 1 is obvious. I'm not even going to dignify 1 with any more time. 1 is obvious. For 2, assume that gamma is non-constant on non-singleton subintervals. Okay. Now let C be a point in AB and take T greater than C. Okay. Now because gamma restricted to TC, not TC, CT, because T is greater than C, because gamma restricted to CT is non-constant, because of this we will be able to find T1 which is there in this interval CT such that gamma of T1 is not equal to gamma of C. Okay, so in fact I want this to be in the open interval, not just the closed interval. I want it to be in the open interval CT. So if this were not true, then for all T1 in this interval CT, then we have gamma of T1 equal to gamma of C, which contradicts the assumption that on non-singleton intervals it is non-constant. Gamma is non-constant. Okay, having done this, let P be a partition. Let P be a partition of AC that contains the point T1. Okay, take a partition of AC that contains this point at T1. Okay, then it's clear that P union let me make a slight change. Ultimately, what is it that I want to prove? I want to show that gamma of T is greater than gamma of C, right? So let P be a partition of AC. Set P1 to be P union T comma T1. Okay, then it is obvious that P1 is a partition of A T. Okay, it's obvious that P1 is a partition of AT. Furthermore, we have this, by definition, the way we have set up things, the length of gamma restricted to AC with respect to this partition P is going to be less than or equal to, not less than or equal to, this, let me write the inequality the other way, which should be better and more transparent. Length of gamma restricted to AT with respect to P1 is nothing but length of gamma restricted to AC with respect to P plus these additional points that we have considered, t and t1, which is norm of gamma of t minus gamma of t1 plus norm gamma of t1 minus gamma of c. Okay. So what we can conclude is, we can conclude that length of gamma restricted to at is itself this is always is greater than or equal to length of gamma restricted to AC comma P plus some positive constant, plus some positive constant independent of the choice of partitions. Okay, plus some positive constant. Now taking the supremum on the right hand side with respect to P, we conclude that length of gamma with respect restricted to AT is strictly greater than length of gamma AC. Okay, so first we took supremum over actually it's better to just combine both steps. There's no we can write this gamma of AT with respect to P1 is this. I can write this is greater than or equal to length of gamma restricted to AT. Yes, now this is perfect. Okay, so net upshot is S of t is greater than S of c. So this concludes the second part, that the arc length is strictly increasing if gamma is non-constant on any non-singleton interval. Now the final and the most challenging part is to show continuity. So fix t in AB. Our goal is to show that gamma is continuous at this point. So fix epsilon greater than 0 and let delta greater than 0 be chosen using the continuity of gamma, such that mod gamma of t minus gamma of x, or rather I should put norms here, norm gamma of t minus gamma of x is less than epsilon by 2 if norm x minus t, or here it's just mod, if mod x minus t is less than delta. This is just the continuity of the function gamma. Okay. Now fix x with mod x minus t less than delta and x less than t. Okay. Let P be a partition of this interval xt such that the length of gamma restricted to xt with respect to this partition is greater than or equal to the length of gamma restricted to xt plus epsilon by 2. Now what is happening here? Things might seem a bit confusing. What is essentially happening is the following. I am going to choose a partition of P such that the partition is so fine that the length with respect to this partition is not that different from the actual length. Since this quantity is nothing but the supremum over all partitions of the quantity on the left, given any epsilon, one second, I made a massive goof up. This is minus epsilon by 2. So given any epsilon, or in this case epsilon by 2, I can always choose the partition so fine such that this is at the max epsilon by 2 distance away from the actual value of the length. This is just the way supremum is defined. This follows just from basic real analysis, basic properties of the supremum. Okay. Now what I'm going to do is I'm going to choose a special partition, not a special partition, I'm going to choose a point on this partition. Let Tm minus 1 be the last but one point in P. Okay. Then because we have chosen that delta originally so small and x is within that delta neighborhood, we have that non gamma of t minus gamma of t m minus 1 is less than epsilon by 2. Okay. Now what this means is that if I consider the length of the curve gamma up until the point x, up until the point t minus tm minus 1, up until the last but one point, and I take this special partition p minus the final point t, this will obviously give a partition of x tm minus 1. With respect to this partition, we know that this is going to be greater than length of gamma xt minus epsilon. Okay, that's because the partition P was chosen in such a manner that the length of gamma restricted to xt with respect to P is at the max epsilon by 2 distance away. But this last point, the contribution from the last term arising in the sum, can be at the max epsilon by 2. In fact, it's strictly less than epsilon by 2. Therefore, the contribution from the rest, which is just this, must be at least this. Must be at least length of gamma restricted to xt minus epsilon. Okay. Now, by additivity of arc length, by additivity of arc length, and the fact that L of gamma x restricted to t m minus 1 is comma p, of course with respect to this partition p minus t, is less than or equal to length of gamma of x restricted to t m minus 1, combining additivity of arc length with this fact, we can conclude that length of gamma restricted to tm minus 1t is at the max epsilon. So this just follows from writing length of gamma restricted to xt as the sum of length of gamma restricted to x tm minus 1 plus length of gamma restricted to tm minus 1 t, and this previous equation immediately gives us that length of gamma with restricted to tm minus 1 t has to be less than epsilon. Okay. Now what does this show? Well, again you apply additivity of arc length. This shows that s of t minus s of tm minus 1 is less than epsilon, because this is nothing but the length of gamma restricted to tm minus 1 t. So we can conclude that if x less than t is suitably close, then s of x s of t minus s of x is less than epsilon. Similarly, we can handle x greater than t. Analogous argument we can give. So net upshot is gamma is continuous. continuous at t. So this concludes the proof that the arc length function S is actually continuous. So the last proof is a bit tricky, so I would suggest that you watch it again and read the notes and make sure you understood the ideas behind the proof. This is a course on real analysis and you've just watched the video on rectifiability and arc length.